The question asks us to find the binomial expansion of cosine theta plus I sine theta to the power of 5, and to give our answer in the complex number form. This question is a mix of the binomial expansion and giving coordinates in polar form. However, it looks more complicated than it is, and all you really need to do is do out your binomial expansion of cosine theta plus I sine theta, and remembering to just use your rules of complex numbers where I squared is equal to -1, and go on from there. The binomial expansion is a method to determine the multiplied out form of a plus b to the n. You can see here when we have n equal to 0, 1, 2, 3 that there's not so many terms. However, you can also see that this is growing each time. So how does it work? First, let us multiply out just in a more full way all of the terms, including if it's to the power of 0 or if there's a multiplied by 1 term, just so that we can see everything. Then we can see that it was based off two patterns that were recognized. The first being with the coefficients, which as you can see is similar to Pascal's triangle, where every term is equal to the sum of the two terms above it. Obviously for the edge cases here, there's only one term above it, but for the other terms like the 2 and the 3, that's equal to the two terms above it. The second pattern that was noticed had to do with the exponents for a and b. As you can see for the exponents of a, it starts off at what n was equal to, and each next term it goes down by 1. Conversely, b starts at 0, and each next term goes up by 1 until it reaches n. We are then given the general formula for the binomial expansion, and you can see here with a couple of terms multiplied out. This is given to us in the mathematical formula booklet. And really what you should remember about the binomial expansion is that there's no great understanding to this. It was pattern recognition that allows for easier multiplication of a plus b to a certain power. You just need to fill in the values and calculate. Going back to the question, we just need to use the formula that's given to us for the binomial expansion. So here we can see a plus b to the power 5 is equal to a to the power 5 plus 5 choose 1, and etc. And simply we just need to substitute in cosine theta for a and I sine theta for b. So writing that out, we have that's equal to cosine theta to the power 5 plus 5 choose 1 of cosine theta to the power 4 times I sine theta plus 5 choose 2 cosine theta to the power of 3 times I sine theta squared, and continue. Fully multiplying that out and simplifying, you can see that we've got cosine theta to the power 5 plus 5i cosine theta to the power 4 times sine theta plus 10i squared cosine theta cubed times sine theta squared plus 10i to the power of 3 cosine squared theta plus 10i to the power of 3 cosine theta squared plus sine theta cubed, and continue. The next thing we need to do is anywhere we see an I squared or higher, we need to convert all I squareds into -1. You can see for the first two terms this does nothing. However, the third term is a 10i squared, so this becomes -10. The next term is 10i cubed, so that's the same as 10i squared I squared becomes -1, and we end up with -10i. I to the power of 4 is I squared, so that's -1 times -1, so it just becomes a +1. And finally, I to the power of 5 is the same as I to the power of 4 times I to the power of 4 is just +1, so we end up with just I. Finally, on the last line, all we need to do is group the terms that have an I with them together and the terms that don't have an I with them together. So we can see that our final answer is cosine theta to the power of 5 minus 10 cosine theta cubed sine theta squared plus 5 cosine theta sine theta to the power of 4. That is the terms without the I. Then we factorize out the I from the other terms, and we're left with I times 5 cosine theta to the 4 sine theta minus 10 cosine theta squared sine theta cubed plus sine theta to the 5. And this is our final answer. Part B of the question asks us to use de Moivre's theorem and our answer to part A to show that sine of 5 theta is equivalent to 16 sine to the power of 5 of theta minus 20 sine to the power of 3 of theta plus 5 sine theta. De Moivre's theorem is a theorem that can be proven via induction, where if we have that z is equal to r times the cosine of theta plus I sine theta, and we want to determine that if we are to bring this up to a higher power, so for example z to the n, then that should be equal to r to the n times by cosine of n theta plus I sine n theta. We take the base case where n is equal to 1, and we know that this is true, that if z is to the power of 1, then that's equal to r times the cosine of theta plus I times the sine of theta. We're going to assume it's true that if we rise it to the power of k, so z to the power of k is equal to r to the power of k times by cosine of k theta plus I sine k theta. And we want to check that for z to the power of k plus 1, that this remains true. Now z to the power of k plus 1 is equal to z to the power of k times by z. And so we're going to fill in for this, that z to the k plus 1 is equal to r to the k times by cosine of k theta plus I sine k theta times by our base case, so r cosine theta plus I sine theta. Using the trigonometric identity that the cos of A plus I times the sine of A times by the cosine of B plus I times the sine of B is equal to the cosine of A plus B plus I times sine A plus B, we can simplify our previous statement down to z to the power of k plus 1 is equal to r to the k plus 1 times by the cosine of k plus 1 theta plus I sine k plus 1 theta. And from that, we've shown that the case of z to the k plus 1 is true if z to the k is true. And then we can go further and say that because the base case of n equals 1 is true, that De Moivre's theorem holds true. So when using De Moivre's theorem, you can say that if your statement of cosine theta plus I sine theta to the power of n, you can change this to the cosine of n theta plus this I sine n theta. To answer this question is quite straightforward. We need to use De Moivre's theorem to show that the cosine of theta plus I times the sine of theta to the power of 5 is equal to cosine 5 theta plus I sine 5 theta. Now we've already used the binomial expansion in part A to solve it out a different way. So we have that our answer to part A is equal to this cosine 5 theta plus I sine 5 theta. Now we're looking specifically for the sine part of this equation. So you're going to look at the I component of our solution to part A and the I component to De Moivre's theorem. And we can set these equal to each other, where 5 times the cosine of theta to the power of 4 times sine theta minus 10 times cosine theta squared times sine theta cubed plus sine theta to the power of 5 is equal to sine of 5 theta. Now remembering that the cosine squared of theta is equal to 1 minus sine squared of theta, we can substitute this in anywhere we see a cosine squared of theta. That gives us that the sine of 5 theta is equal to 5 times 1 minus sine squared theta, all to be squared, minus 10 times sine cubed theta times by 1 minus sine squared theta, all to be squared, plus sine theta to the power of 5. Simplifying this out, we end up with 5 times 1 minus 2 times sine squared theta plus sine to the power of 4 of theta times sine theta minus 10 sine cubed theta times by 1 minus sine squared theta plus sine to the power of 5 of theta. Eventually this solves down to the sine of 5 theta is equal to 16 sine to the power of 5 of theta minus 20 sine to the power of 3 of theta plus 5 times sine theta. We're being asked to show that when theta is equal to pi over 5 and when theta is equal to 3 pi over 5, that these are solutions of the equation 16 sine to the power of 4 of theta minus 20 sine squared theta plus 5 equals 0. Now it's pretty obvious that this equation is very similar to what we just solved in part B. However, each component of the previous equation has been divided by a sine theta. So 16 sine to the 5 theta has gone to 16 sine to the 4 theta. So what do we need to do here? Well, let's start off with what we solved in part B, that the sine of 5 theta is equal to 16 sine to the 5 theta minus 20 sine cubed of theta plus 5 sine theta. We can factorize out a sine theta from each of those, and we end up with the sine of 5 theta is equal to sine theta times by what we're being asked for in part C, the 16 sine to the 4 theta minus 20 sine squared theta plus 5. Now, this equation goes to 0 when the sine of 5 theta goes to 0. The sine of 5 theta goes to 0 when theta is equal to k times pi all over 5. Basically, the sine of an angle goes to 0 whenever that angle is 0, pi, 2 pi, 3 pi, etc. Now, because we have 5 theta, we're then going to divide that by 5. So it's some multiple times by pi divided by 5. Then solving this further, we know that then 0 is equal to sine theta times by 16 sine to the 4 theta minus 20 sine squared theta plus 5. Now, in order for this to go to 0, as this two things multiplied together, either the sine theta goes to 0 or the thing inside the bracket goes to 0. Now, we know that our solutions, so pi over 5 and 3 pi over 5, if we plug that into just the sine equation, so sine of pi over 5, that is not equal to 0. And the sine of 3 pi over 5 is not equal to 0. Therefore, the thing inside the brackets must be the thing that goes to 0. We know already that theta is going to be some multiple of pi all over 5, so therefore those two solutions must solve the 16 sine to the 4 minus 20 sine squared plus 5 equation. For part 2, to show that the sine of pi over 5 times the sine of 3 pi over 5 is equal to the root 5 over 4, this comes from a rule in quadratic equations where the product of roots is equal to c over a. Now, if we treat the equation 16 sine to the 4 theta minus 20 sine squared theta plus 5, it's a quadratic equation where imagine your x is equal to sine squared. So x squared would then be sine to the 4, your x would then be sine squared, and your c component would still have no sign. So that equation can be written as a quadratic equation. Therefore, if we know the roots of that quadratic equation are sine pi over 5 and sine 3 pi over 5, then multiplying them together should give c over a. I've shown here how we get that the product of the roots is equal to c over a. I'd encourage you to multiply this out yourself to make sure that it is right in your head. But essentially, using the quadratic formula, where we have minus b plus or minus the square root of b squared minus 4ac all over 2a, that is your two roots. You have minus b plus and minus b minus. If you simply take those two roots and multiply them together, you'll eventually get that you have c over a. Knowing this, you should know that our roots are sine squared pi over 5 and sine squared 3 pi over 5. If you multiply that together to get c over a, so multiplying that together, we get 5 all over 16. Next, taking the square root of both sides, we'd have that sine pi over 5 times sine 3 pi over 5 is equal to the square root of 5 all over square root of 16, which is 4. Thank you so much for watching. I hope this tutorial made things clearer and helped you tackle this question. Don't forget to like, subscribe, and hit the bell to stay updated when more questions are answered. If you have any questions or need any more help, please drop a comment below and I will get back to you. Until next time, keep practicing and good luck.